All right. So I did manage to get the survey up there, so I'd really appreciate your feedback. Probably won't take you very long, but your feedback definitely helps. And over the years, students' input and questions have really helped develop, change, validate this stuff. So always be willing to ask those questions. It really helps. So that survey's there. Yeah, if you'd do that, that'd be great. And if you can get any your work in here by Sunday, and I'll look that over if you've done the work and all, and you're in there. I'm not evaluating how good you've gotten, but just that you've been in there. And I hope you do push yourself to really get this. It is going to pay off, I think, in a very big way. We really have done about the first month of class. And then as you get into chapter 7, which I hope you do, I think you'll see force analysis there, which is another big topic and very useful for Zach and anybody else that's doing physical therapy. It's a big thing. And it's very concrete, and it follows a lot of the math that we've done. And as I mentioned in my email, chapter 5, I had to get the preliminary out as so we could start using it, because we wanted to get this course going, because people need it. And so I got that out, and I wasn't able to complete the solution for chapter 5, but they are in the first edition. But chapter 7 shows you how to deal with vectors in the context of forces. And so here I've got this picture of forces we talked about last time, and we said, like, for example, when we talk about kinematics, describing motion, I mean, that's huge. That really started things off around 1600, Galileo, and so on. And there we talk about an earlier state and a later state. We think of a video and we've got earlier state, and then go 1, 2, 3, 4, where we want to analyze it. And that takes some training, and you guys have been engaged in that training, so it's getting more familiar to you. Very hard at first, especially when it comes out so fast. When we do force analysis, we often say, okay, freeze at one time. This thing might be moving, I don't know, I can't tell if it's moving up, moving down, increasing speed, decreasing speed. It's just a snapshot. We often take a process, take a snapshot at that moment, look at all the pushes and pulls on that object. And so you can find them. It's there's a little trick to it. You just look at whatever's touching it. That's what's pushing and pulling on it. But it's got to be a direct contact. And then there's the weird forces, the first one being gravity. Then there's the electric force, magnetic force, and then usually we don't deal with it much, but the nuclear forces, the nuclear weak and nuclear strong forces. And those are the only forces that we know of that exert a push or pull without touching. And that's deep and curious and all, and fun, but you can't really understand that until you get into this type of analysis. So I look for things that are touching. In this case, this red block, it's only the surface. So it's exerting forces, and I talk about those in chapter 7. And again, you don't have to be entirely clear, usually you aren't the first time through, to have benefit from that, because as you go through it in your physics course, it'll be useful. I will say in chapter 7, I also explain friction in a very unique way. And so I just kind of invented a term and showed you some things more explicitly than books do, and gave you a way to think about it. So that's often a source of confusion. Friction, something called the normal force, etc. So as you go through the course, if you've gone through it once and then you go through the course, you kind of read that over, it'll be useful. Okay, so for example, I've drawn the force of gravity pull straight down, always vertically down. No matter what you do, gravity pulls straight down, which is a really weird thing. But sometimes you got to set aside that coolness or the weirdness or whatever it is and just move forward and use it a bunch, and then you can process that. And then we can break it down. Now, remember that when you have vectors, so you draw your situation, you draw your vectors. You can't add a force vector to a velocity vector. That doesn't make any sense. You know, that's, it just doesn't, the two aren't the same thing. So you can add velocity to velocity. You can't add velocity to acceleration. They're related, but you can't add them. How do we do it? Well, we're going to talk about adding and subtracting vectors today a bit. And again, it applies huge when you get to force analysis. It's just, you just do it over and over. And one thing that you've come to realize, and it's a big hurdle because people come into a physics class, they're not used to this much detail. They're not, and some of you mentioned that right away and saw that, and it's true. They're not used to laying this stuff out. They're also not used to having a puzzle where they got to figure it out. I mean, you got tools. They're kind of used to, here, just do this, then punch this and punch that, and then that's how you do it. You go, okay, I'll punch that. Okay, I'll do that over and over. Now I know how to do it. Here, it's not a one-liner. Don't plug numbers into an equation. That's, you know, kind of not a very useful exercise. And in fact, your pay grade goes up with the more puzzles that you're asked to solve, whether it be political puzzles or administration puzzles, or you're in the counseling department, they got to solve puzzles. And so dealing with that. In this case, when we're dealing with vectors, we need to choose a coordinate system. Now you could choose, this is my grid, and you can break it down into X and Y parts. Still haven't done what I was thinking about doing. And you do it how, any way is fine, but some ways are better. So choosing the direction along that it's moving along the incline is a really good way. So I draw my grid, I have my vector, I draw my coordinates, choose my coordinates, and then I draw lines through the tip and the tail, parallel to the Y and parallel to the X. I get a box. I can use either triangle, and I just start working it, breaking it down. I can't do it in my head. I can't just know the answer. I just look. And so that's another theme here and another development, realizing that the answer isn't here. You know, if I ask you what's the capital of, I don't know, wherever, Tennessee, you know, what is that? You know, maybe it's Nashville, I don't know. So that's just a memory thing. But here, you look, you know, you look and you figure it out. If I ask you what color pen am I holding, you know, well, you look, you don't figure it out. So too, with the physics, it's kind of this combination. You got to read it, you got to lay it out, and you got to see it. And it's very much like the puzzle pieces that you just move around. Like you dump a pile of puzzle pieces and you go, what's the picture of? I don't know, I got to move it around. I'll find out once I put the pieces. And that's where this is. And so it's powerful, but it's challenging. You guys get that though. So just even having that awareness gives you a huge head start. All right. So we said that any vector can be broken up into parts, and we can write that vector in polar form, which is the total amount. For force, it's the strength and the direction given by some angle. For velocity, it's the speed, and the direction is the direction of travel. So any vector can be treated this way. Electric field, magnetic field, all kinds of crazy vectors. Torque can be a vector. There's all kinds of crazy stuff, angular momentum, etc. And you all deal with it the same way, mathematically, with different meaning. So we've got polar form, amount and direction, or component form, how much in that I hat means in the X direction, and the J hat means in the Y direction. Again, some books might use X hat and Y hat. And you break it down. You got to look at the plus and minus sign by looking at your drawing and your coordinates. And once you get used to it, it's just, there it is. Stop me if you have any questions. We can go back to chapter 5, where I'm still doing kinematics, and we can talk about velocity. Velocity at any moment. So if you're traveling along a path, you've got a velocity. Now I look at this picture and I go, hey, traveling faster there. How do you know? Because this is drawn longer. Slower there, faster there, and then slow down going into the turn, whatever. So I can see that. And velocity is always tangent to the path. That is, if you hit ice, you'd go this way. If you hit ice, you'd go that way. And if I look at that picture, I don't even know. I don't know whether this is vertical, or maybe I'm looking down from a drone, looking down on a flat ground, and it's really rotated. So it's hard to know. We have to make that clear. And those details matter, you know, because there could be all kinds of situations. But nonetheless, at any moment, I can have a speed and a direction. That's polar form. That would be, for the triangle, the hypotenuse and an angle. Or I can say how much in the x direction and how much in the y direction, depending what coordinates I choose. Now, another way of doing it, and really more useful, is to say how much, and this means in the x direction, plus how much in the y direction. This should have units. When you put numbers in, always put units, and these components have units. Okay, so you could add velocities, and that's section 4. You probably will touch on that a bit, and you could look at that, but I think going into chapter 7 would be useful, and kind of break it up a little bit too for you. So whatever you can do for the rest of the summer will always add value and make life easier. But chapter 7, I think, is a pretty important one to go through. And then there's 6 and this other stuff. So you can add velocities. For instance, when you're walking on a bus and the bus is moving, your total velocity over the ground is your velocity of the bus plus the velocity of you in the bus, you know, or in BART or on a boat or whatever. They're useful. I'm going to make this comment too. In your career, who knows whether you'll ever use this? Some people will. Taking a step before your career, there's upper division. Now, a lot of times you do use this kind of stuff in upper division. Certainly engineers do, but biologists can too. In fact, I've talked with many doctors, surgeons. You get chatting and whatever, and you know, you just go, "Oh, what do you do? Oh, you're a surgeon. Oh, so what'd you think of physics? You know, or I'll say I teach physics, and they go, "Oh, the thing that they learned, the most important thing they got from physics was how to problem solve." They always say that. Also, you may use certain concepts like volts or current or whatever. Okay, so vectors are just anything with direction. And we divide and conquer. We break them into parts.
Is that with electron flow?
Electron flow, yeah.
Proton flow, your choice?
Yeah. I just read an article about how solar wind might, when you have solar flare-ups, they could create earthquakes. It's not clear, so it's being explored, and I think there's going to be a lot more work to be done. So it's interesting. And yeah, it was. So let me show you this as a preview for what we're going to do. I'm going to talk about Jacob's question, chapter 5, number 12, and show you how this can work. And then I'll walk through another example. And I'll either use this recording or another recording. I'll try to post it to YouTube if you need to look at it, but just try to get it. You know, and again, the way you can get most value out of any lecture is to preview. Use those things to save yourself time. You know, I finally got that. I realized I'd always be mad at myself if I didn't do it because I just made more work for myself. I made it hard. I haven't got time for more work. I can't add more time. I got to preview. I got to catch it while it's going flying by me. So let's take a look at chapter 5, number 12. All right, cool. Yeah. All right. Just gonna write this up here. Yep. All right. So what I've given you is the component form of these positions. Let's get rid of this. Now, one key is that if you can't put things in the same units, you can't add and subtract them. You can relate them, maybe. They're equations, but okay. Position number 1 from some origin is equal to 3.0 mi, so that's miles, I hat in the x direction, minus 2.0 miles in the y direction, so that is opposite the y direction. R2 is equal to negative 5.0. Really make that negative. I don't want to drop that negative sign. Negative 5.0 miles in the x direction, plus 7.0 miles in the y direction. And then R3 is equal to, and it's given as negative 4.0 miles in the y direction. And here's the key. So what I want you to think of, and this, because I threw that in there because it does bother people. Just think of it this way. That means the position is 0 in the x direction and negative 4.0. So there is an x component in a way. I mean, it's 0, but you can still think of it being there. So I'm not going to write it. I mean, you can write it, that's fine, just as long as you realize that that's true. What would that mean on a graph? Well, if this is my x and this is my y, then the position would be 0 in the x and negative 4 in 1, 2, 3, 4 in the y. So that would be position 3. Sorry.
So if you're writing it in its polar form, would that mean you put the y in for it, and stuff like the hypotenuse, you put y in for it?
Yeah, okay. In polar form, and that's also an interesting little thing. So, and this is a case where you can do it a variety of ways. In polar form, you would say, you could either say negative 4.0 miles, and the direction would be in the, I don't know, y direction. Or you could say 4.0 miles, and the direction would be the negative y direction. So that negative sign comes, sometimes you could float it a little bit. And, you know, what we've been doing here is actually addressing, in a unique way, your sophistication with math. You're not using math. You're now using math as a language. And that's really not taught enough. It can be a little bit. And sometimes we just can't digest it when we're younger too, because this is a pretty sophisticated, I mean, this changed the world. And so that's often the missing gap. You know, you can get some of these concepts, and maybe you can do the algebra, but to put the concepts in the algebra and think in terms of process, That's profound. And you guys can do it. You've been doing it. Keep going. So yeah, polar form would be how much and in what direction. You could say it a variety of ways. And you'll see. You don't have to come up with it entirely. If you've got that, that's great. So let me do this real quickly. And then the question is, what is, Jacob, your choice? Which one do you want to do? 1 to 3 or?
I wanted to do 2 to 3, but
Okay.
if
Yeah.
I assume it shouldn't matter, the process is the same.
Right, that's right.
Okay.
And once you get that, and the initial ones, so this is huge. And like anything, everything seems so enormous. And then once you work it out, you go, okay, I got this. Yeah. So the change in position from 2 to 3 is the later 3 minus the earlier 2. Okay, well, how do I do it? Well, you can do it with arrows, and I'm going to show you that here in a second. But components are beautiful. You see, that's equal to now I'll show you this again. Remember how we had V2 is equal to V2x I hat plus V2y j hat. So we put an X and a Y on the vector. That part, X part and Y part. Position is the only one that I can think of, only vector I can think of where you actually make it a different name. Instead of calling it R3X, you call it X3. Plus Y3 j hat. Oops, yeah. And that's what this vector is. And then you subtract this vector. Okay, whatever, it doesn't matter. Which is X2 I hat minus plus Y2 j hat. And so the great thing is, and again, you're disoriented initially, but then you get it. And you lose your pen cap initially. Seriously? Okay, anyway. You can still do this. Equals. The parts in this X direction all get to be combined. So I can do X3 minus X2 in the X direction. Oh, there's my cap. I found my cap. I lost my pen. Okay, no. I got it. Because the minus goes here in here. So plus Y3 minus Y2 j hat. Ooh. Okay. And the key is that X3 is 0 minus. Now, I want to point this out because this is actually a particularly good example because what you have here, I look up here, X3 is 0 minus X2. X2 is negative. So what I do to be really safe is minus a minus 5.0 miles. Don't forget the units. Don't be sloppy with that. It'll cost you and you'll be mad at yourself. Y3 negative 4.0 miles minus Y2. See, I'm not doing it in my head. I'm just looking up here. Minus 7.0 miles j hat. What does this give me? This number here is delta x from 2 to 3 I hat plus delta y 2 to 3 j hat. That value is that. And I'll show you this. Oops, sorry. I'll show you this with another example here. But that's how you do it. You just divide it, and then you can add and subtract the x parts separate and the y parts separate. You can also do kinematics and just do the x motion separate and the y motion separate. So that's how we divide it up. It's all about drawing those triangles. Does that make sense?
Yeah, it makes sense.
And then if you want the total, if you want to go to polar form, you take this squared plus that squared square root. That's the total. And if you want the direction, you draw this, and then use inverse tangent. So it's the same thing over and over. And the beauty is that means that you can handle that, and you can then think about the physics you're learning. Okay. Good stuff. There will be times that you will feel stumped. You will need to ask questions. This stuff is challenging, for sure. I say it literally changed the world. So don't feel bad about that. Just get in there, grind and struggle over and over. You guys have been great about supporting each other and kind of realizing that. That's all you need to succeed, and then you got to do it, get it done. All right, let me show you something else. Similar. This is a good lead-in. Thank you, Jacob. That was a perfect question. I don't know how that happens, but somehow you guys managed to ask these perfect questions. All right, check this out. I'm just going to draw. Here's the path. The path I've got here let's do it this way. It doesn't matter which way you go. Now, until I tell you, when I draw something here, you don't know if this is a picture of everything that's happening horizontally or there's vertical. Right now, it doesn't matter. So here's some path. Be a spider walking on the thing. And let's just start here. And I go like this. Get way down here. Now, if I just saw that, I wouldn't know which way it's going. I mean, it could go from here to, so it could go 1, 2, and back to 3. I don't know unless it's labeled. I could start here and go, I don't know. So I need to, 1, you can put it inside, or however you would do it. 1, 2, let me do that. Well, yeah, let me do it inside. 2, and 3. Let's work with displacements. And again, I encourage you to work with forces in chapter 7. All right, let's see what we've got. Let's talk about displacement. Now, distance is along the path. And if you know your odometer on your car, it tells you how far you went. It doesn't care which way you're going. And the distance is what we need for average speed. But displacement, well, displacement is straight away from earlier to later. So this here would be the displacement from 1 to 2. From the earlier, so that's the tail of the vector, to the later, and make sure you always have an arrowhead or tip on your vector. So that would be delta r. I'm going to go ahead and write this like this. 1 to 2. And really, Jacob, that was such a perfect example. And then I'm going to go over here and go, okay, Well, then this would be delta R to 3. I wanted to distinguish this because delta R from 1 to 3 is this. And really, if you get this example, you've got it. You've got most of what you need here. And you can go on stuff. From here, now, you have to pay attention. Now, you might not think of doing something, but sometimes you'll do stuff and then you're not sure and you have like this little confusion. A lot of people will go like this, here, here, and then they'll go back this way and put the arrow here. But if you think about the meaning, I'm talking about the displacement from 1 tail to 3 tip. And I can't tell you how many times I've seen it done the other way. So why? Because people are overloaded, confused, or they just have some thought. And sometimes we'll have a preconception of what it should be. But we really have to look at what the meaning is. Everybody with me so far? Good, thumbs ups?
Yeah.
All right, cool, nice. So that's all I'm talking about, right? But the beauty, as I say, is any vector, forces, velocities, whatever, any vectors can be done kind of in the way, it's this way, but velocity vectors in the direction that you're traveling and has a length for the speed. Force is the direction of the push or the pull with an amount of the strength of the push or pull. Displacement is from an earlier state to a later state. They all mean different things, but you still divide and conquer the same way. Okay, now what do I need? Well, two things. You could use a ruler and a protractor and measure angles and things like that. And that's called graphical analysis often, or arrow analysis if you want. But you can also do the calculation. Now we need to choose a coordinate system. Let me just keep that kind of straightforward right here and just call it, I was going to do this. Yeah, well, yeah, all right, fine. And you know, it doesn't have to be up and to the right, but I'm going to do this. I'm going to put a plus y here. Colors are kind of nice, but you can overdo it too. And a plus x here. All right, that's my choice. You could choose something different. You'll get the same answer in meaning. Meaning of your answer will be the same as the meaning of my answer. All right, now watch what we're going to do. We're going to do the grid method. We're going to put everything together, and then you've got, for Physics 120, for that series, I want to say, I'm pretty sure, yeah, you've got everything you need. For the Physics 130 series, you learn how to multiply vectors. And there's a couple of rules that are useful. You can make up all kinds of rules, but there are two that are useful. And you could do a little bit more. But that's crazy. Getting over this hump, not having this struggle with this in the middle of the semester. Oh my gosh. You guys are being very good to yourselves. Okay, so notice this. In what I want to find, for example, I mean, the question, I don't know, the puzzles are always, I'll give you some information, you find the rest. That's how we do it. So I might take a look at the displacement from 1 to 3. And thanks to Jacob, we took a look at a good exercise, number 12, one particular way. Now notice we have vector arrows. We also have the vector variable, how we write it. And I try to be really careful about that. Books often don't say that very clearly. And then we've got the arrow, we've got the variable, we've got the polar form, and we've got the component form. 4 ways to talk about a vector. If you think about it, if you go somewhere, you start here and you end up there, but you took a break or something, you had to drop something off, pick something up, then the displacement from 1 to 3 happened because you went from 1 to 2 and then 2 to 3. So the displacement from 1 to 3 is the displacement from 1 to 2, and I put a little half arrow up there. You can put a full if you want, easier to write, plus the displacement from 2 to 3. Does that make sense? That statement?
Yep. It's going in the positive direction. Probably both orange, huh?
Yeah, and so you just go, all right. Now I want, but how much is it? Well, you can measure the angles and measure the lengths and do all that stuff, or you can calculate it. Well, how do I calculate? I mean, that's a fine statement. And I'm making a statement in mathematical terms. Well, what I do then is I say, oh, the key is you divide and conquer. And so you say, that's equal to, give myself a little room over here, this guy plus this guy. Well, what is it? Well, you're going to need to break it down. So I can write it symbolically without doing it, but this is true, right? This is true where I say it is, now, it's the one vector where the name changes. So that's, oh, wrong color. Delta x, changing my x from 1 to 2 in the x direction. So you move some in the x direction, and you move some in the y direction. And then this one moves some in the x and some in the y. So plus delta x 2 to 3 in the x direction. That's all the I hat means. We say I hat, kind of like I hop, but I hat. Plus delta y 2 to 3 j hat. And so you just do the little things, and you do it enough, it's like, oh yeah, obviously. Oh yeah, that's what we're going to do. We're going to divide these up. So I notice the name change here. I don't do Rx, I just do X. It's the only place. X is for position. Y is position. Don't use X for just an unknown. Really been beating that drum with math folks. Now let me show you something. Just jump in. It's not an interruption. Participation. I want to know how much in each direction. What do I need? Haha, I need this, right? And then I can line it up. Oh, I chose it that way. Okay, fine. So I go over here and I go, all right. I can count boxes. How much in the X, how much in the Y? How much in the X, how much in the Y? Now I can do that. You know the game. You're starting to get used to it. You draw a line for each vector through the tip and tail parallel to your coordinates. So I'm going to go here, parallel to X, and try to make nice drawings. Now, some people are better at it kind of by nature than others, you know. That's fine, but just try. Also, we're doing these puzzle pieces. So I want to make a point here. Suppose I give you a 1,000-piece puzzle. You know you can solve it if you put the time in. You're getting paid for it. You really want to solve it, right? Now, if you take those 1,000 pieces and you put them on this one piece of paper, and you try to solve it on this piece of paper, well, you know, you quickly say, I need more room. So don't cram your work on, use pages. Make it clear so you can find your little mistakes with the negative sign and stuff.
We
Right?
can realize that
Yeah.
after some of these, that more space is required.
Yeah, and you know, and we learn by doing, right? I mean, I did too. I learned that too. In fact, you know, there are stuff in upper division that would take me 10 pages of algebra. You know, it was like, or whatever math and things. So you just got to lay it out. And the other great thing is you can catch your mistake, or someone else can catch your mistake, and it's just a good way. It's a professional way to do it. People really value that. It's valuable. Okay, so give yourself room. Make it as clear as you can. You know, but don't overdo it. There's a balance. Okay, through X, through the tail and tip and the Y direction. Let me make that a little darker here. Right. And the Y direction through the tail and tip, I've got a rectangle, which means I've got two triangles. Make it kind of reasonably, right, perpendicular. The components are always from, now this is going to be cool. It's going to be cool. It's going to be cool. From the tail. I like to use dashed lines for the components to the tip. So that is my delta X 1 to 2. Delta X 1 to 2. That much, that way. And my delta Y, because this is the grid method, from 1 to 2, I can do it either place. I can do it here. It doesn't matter. Or I can do it up here. For certain reasons, I'll show you why I do it over there. But okay, so that's what that is. I can see it on my picture. I can write it in an equation. Then I'm clear. I know what these things mean. They mean that. And then over here, I can see that too. Just now I start getting faster. Oh, through the tail and the tip, parallel to my X, grid method, through the tail and the tip, parallel to Y, from the tail to the tip, along that grid, delta Y 2 to 3, delta X 2 to 3. This example does a lot, I think. Everybody okay so far? I'm saying the same thing a lot of different ways, coming at it different ways. Crystal clarity so that we get it right and we understand it. What's the displacement from 1 to 3? Well, if I took this brown path, I stopped, it's the same as the displacement straight from 1 to 2, and then plus 2 to 3. I can show the arrows. I can write the variables. I know what I want. The way that I can't add these numbers, guys. You know, if this is a length of 5 and this is a length of 8, I can't add those because this isn't 5 plus 8. They're not lined up. It doesn't. But you could do it. You can't do it in your head. That's why this is. If you do it in your head, who's going to pay you? Why would they pay you? So I can represent it, but I gotta bring out the details now. Oh, this is this much in the X direction, whatever that is, and this much in the Y. This is this much in the X, this much in the Y. Oh, wait. If they're in the X direction with each other or opposite each other, I can add them. So I get to do this. That's delta X 1 to 2 plus delta X 2 to 3 in the X direction. I can add the blue ones. Plus.
Is that combining like terms?
Yeah. In this case, combining all the terms in that one direction with or plus or minus that direction. That's what you do with forces too. They're pushes and pulls. You add up all the pushes and pulls in the plus or minus X direction and all the parts of, I should say parts of the components of the pushes and pulls in the X direction. Then in the Y direction, you'll see in the solutions in chapter 7 how I make a table. And when you're training your mind, you know, you want to use that table. It'll catch all your mistakes and it'll guide your thinking, and you'll do the steps rapidly. So, you know, delta Y 1 to 2 plus delta Y 2 to 3, J hat. Now I'll remind you again that no book as of now, aside from mine, uses this notation. I would like that to change because it's really, I think, helpful. And I think you guys, this is a pleasure for me because I get the chance to actually be able to work with you and train you.
This is the only way I know it, so that's the only way I'll be doing it.
And I know, yeah, just do it your way, man. And you may, honestly, some professors need to be taught this. I mean, I had to develop this and I had to think about it because I used to do it the way, you know, you do it, but then people are confused, and then you start asking them why they're confused, and it's not because they're idiots. It's because it's confusing and because it's unclear, and there's a lot going on. So maybe that's our job to try to sort that out. And good notation is, I mean, I got lots of examples. One of them being Einstein, where he thought one of his greatest contributions was this notation thing. I mean, it's important. It's really important. So, okay, check it out. Check it out. I'm going to show you two things. So this, guys, this thing here, that is delta X from 1 to 3. I'm going to show that to you. That's delta X 1 to 3 I hat. Let me show you. Let's go up here. Delta X 1 to 2 is, oh, it's that blue part, right? You see that right there? It's that much, this guy. And delta X 2 to 3 is that blue part. And this plus that is exactly the delta X of my red one. How do I do the red one? Grid method. Through the tip, through the tail, tail, tip. Now I got this triangle. I don't know, I could do it in red. And how much does my displacement from 1 to 3 go in the x. This plus that is delta x 1 to 3. You guys see that? You can see it this way and you can see it that way.
Crystal.
And now I can look at this, and this is brings up a little interesting thing, which is why I did this. Well, but I can do it manipulating the symbols, but now I know what they mean. And too often people fall into just manipulating symbols. So this displacement 1 to 2 in the y plus displacement 2 to 3 in the y. You got the language, you got everything. Delta y 1 to 3 in the y direction. How can I see that? Because 1 to 2 delta y. So there's delta y 1 to 2. Same thing over here, but I'm gonna draw it over here. I'll show you why. Delta y 2 to 3 is down I like dashes. 1 to 2, 2 to 3, delta y. It's a mess, right? I might, and sometimes I got to redraw. It's like, okay, this is getting way too messy. But this, I think we can get there. Notice that delta y 1 to 2 is positive, but delta y 2 to 3 is negative. The difference between those two is my delta y from 1 to 3. Now it's really getting messy, right? This is 1 to 3. Delta y, I don't know. Delta y 1 to 3 is positive this plus negative this, which ends up being this. This is a positive number. This is a negative number, but I put plus in here, and I know that that's going to end up being a negative. And whatever I get, that's going to be negative. That's going to be positive. Whatever, it works out. Let's look at it. Every situation is different, so whatever. I think there's only one more thing, and then we've got this in the bag. Any questions? Just let me give you a minute to look that over and see who else came in. I know I saw Draco. Let's do it this way. Mm-hmm. All right. We got Jack. And Draco and Claire. Look it over or take a break. Alex, yeah, gotcha. Let's see, Nicole, good, Nicole. Good. Eric, Zach, Jack, Jacob, Draco, Claire, Ashley, Anthony, Alex, Richard, go. Now this is all, and I did this, you know, sequence on purpose. It's a little unusual, but I think it's effective to start with getting components just with a position vector, then build up to displacement and talking about adding and subtracting. Section 4 is adding and subtracting velocity vectors and relative motion. I think when you get, we often do it just a little bit on relative motion, but I do think that section will really help because that's often confusing. Some things aren't said often. And then section 5 of chapter 5, I think is probably only useful, mostly useful for physics 130 types, engineering and stuff. But I would go ahead and jump to chapter 7 for sure. And then if you still have the book for when you do relative motion, you can read it my way. Any questions? I got one more thing to do. And then, again, the reason I like displacement here is because it's kind of concrete what the meaning is. I can show that picture. When you start doing velocities like this and adding them like that, it's kind of weird. And maybe even forces because but you still do the same thing. Okay. Last bit, jump in if you need to. Check this out. So what am I looking for? I don't know. This is just a general thing. I'll give you some and you look for the other stuff. So you just take it and see where it goes. But notice I've got the total amount that this red one goes in the X and the total amount the red one goes in the Y. If I want to know how much total it is, how far away 3 is from 1 straight, how do I do that? If I have this much and I have this much, how do I get this much? If I have that much, that's the X, the Y, how do I get that?
Jason,
Hmm?
that's the hypotenuse over there.
It's the hypotenuse. So how am I going to get that hypotenuse?
Pythagorean theorem, huh?
3 that squared plus that squared. Polar form. You know, what do you want? I'll give it to you. Maybe you want both. Fine, whatever. And what about the direction? Direction's hard sometimes to talk about. It depends. Like projectiles, we often talk about the amount up or down from the horizontal. And I got a little thing about their north, east, and west. And, you know, you just go around. Initially, it's confusing, and you just work it. And if you start learning, like, whenever you're confused, you just keep working on it, and you're going to get it. And if it's valuable to you, just do it. How do I get the angle? Well, which angle do you want? You know, it's like, I don't know, whatever. I could want this angle. I could call it theta. We often call it theta or alpha beta. And that angle is the same as that angle. Or I could want this angle, the complementary angle. A lot of times we'll use the letter phi, Greek letter phi, P-H-I, and some people say phi, which is sort of anglicized, but it's a Latin. So it's phi, not phi, but whatever. And of course, the letter that, we say pi, but it's really pi, and it's Latin, so it should be p. Whatever. How do I do this? Well, I do the inverse tangent. I highly recommend the absolute value. of opposite over adjacent. For theta, opposite's delta y, adjacent's delta x. For phi, opposite's delta x, adjacent's delta y. It's flipped. Whatever. Either one. They add up to 90. If you get one, you got the other one. That's it, right? Definition of sine, cosine, tangent, Pythagorean theorem, draw the grid, choose your coordinates, think about the physics. You got the method. Now you get to think about the physics and learn the physics. Math isn't in your way anymore, and you've learned how to connect physics and math, and that was our, in one line, that would be our entire goal of this class. It's the missing piece. But along the way, man, you guys are going to be bullies. but the good news is, and for very good reasons, at this level, in my opinion, in lower division, it should not be curved, and we don't curve in our department. I've had classes where I had one class where almost everyone got an A. In physics 130, that was crazy. I was going, what? I mean, they worked really hard and they worked together. It was crazy. And I've had another class where almost everyone got a C. And I was going, what? But, you know, and sometimes people can bring each other up or bring each other down. Any of you in physics in your classes will be able to help bring each other up, and it won't cost you anything because it's not competitive that way. In upper division, it generally does get weighted, and at university, people don't teach much. You know, we teach like 5 classes a semester. They teach like 1 class a semester, and they don't work with the students because they got TAs or graduate student instructors. So they just average it. Sometimes the average at Berkeley, sometimes physics average might be 20%. That's a bad exam. You need to write another exam or something. 60% can be the highest score, and that's an A. Then you get an A. So you got to kind of get a little thick-skinned. You got to know you're in the game. You got to be in the game. You got to be active. You got to go for it. This is your career. This is your life. It's worth it. You're getting real. You're picking it up. You're picking up that steam. You know, if you work these problems and everything, the payoff, as I say, you may not do problems like this in your career, and that's fine. If you're in engineering, you will do stuff like this in upper division, but you still might not do things like this in your career. You might. But the way of thinking and the detailed thinking and the problem solving is huge. And in physiology and stuff like that, you do see some vectors occasionally. You do see some of that stuff. And so it will give you a powerful tool either way. But nonetheless, you got to get through physics 120, and you got to do it. But it'll be valuable in its own right. And knowing you can do it is I think half the battle. Certainly true for most of us. But you got to have a path, because you know it takes that long. How are vectors?
Vectors.
Things with direction. Yeah. Yeah, you divide and conquer. Go round and round. It's a lot, right? So initially, of course, it's confusing, but keep doing it. Keep looking. I'm sorry that you don't have those solutions, but you, like I say, then I realized, oh yeah, that's right. I got the solutions in chapter 7. So just, you know, do what you can here and then go to chapter 7 and work those. And you'll really start getting used to it. And that should help a lot. So Chippewa, and I think creating a schedule, a daily schedule is good, and also working with each other is good. I don't think I told you guys this. I told the morning class this little example. So I was taking a class in graduate school on electromagnetism, and it's out of this book, kind of a book, thick book, whatever. But anyway, the red book. I think they changed colors. Jackson, and it's really challenging, very challenging course, and oftentimes the people teaching it can't do the problems. So it's like, oh, great. Yeah, I'm confident now. And of course, it depends on who you take it from. The book is written by a guy that was at Berkeley. The person I took it from, she was an astrophysics person studying the inner workings of stars and theoretically modeling that. She was known to be particularly hard. And but you know, I really liked her and was happy with that. We had a small class, and we had a midterm that was a take-home midterm, and the deal was an honor system that you wouldn't look at other research. There really aren't any other resources. Like, where are you going to find that? Oh my God, I just remembered something. Hilarious. But all right, maybe I should tell you. I'll tell you after. So it was a take-home, and you weren't to talk with anybody else. I don't think anybody did. I didn't. But it took me 10 hours a day for 7 days to do this week take-home midterm. I mean, and you just sit there and go, I can't do this. I know. Okay, well, there must be a way. Let me just read this again. What's this mean? What's this? I have no. And so by the time we were done, we were wiped out. I mean, we got back to class, and for a week, we, you know, none of us did anything. It was like, did you do this? Did you? No, I have no idea. I'm totally lost. It's like, no, I'm still recovering, man. I had to go buy groceries and do laundry and whatever. I mean, we were wiped out. So here's the point of the story, is that this guy and I said, well, let's get together and start working on this. And he lived in Marin, and so I'd go over there, or he'd come over here, and we would just sit next to each other. And you know, we didn't have face masks. We would sit next to each other, and then you get you're just kind of working on it, and then you get stuck, and you go, well, what about, did you? Oh yeah, oh that means that. Oh, and we go back and forth, and man, it started rolling, and we're going, why didn't we do this all the time? And there are studies that support this, that in STEM in particular, which is quite challenging, if you're not working with people, you're not learning to work with people, which is really important. And it's more about, sometimes often more valuable than being the sharpest person, you know, the quickest on the stuff. Being able to work with people is huge, no matter what. And of course, you'll learn more and more rapidly, and be able to survive sometimes by doing that. So I encourage you guys to either try to Zoom with the free Zoom or whatever, you know, and check in with each other. What'd you get? You know, and you could look at something, and then it's like this little thing. Oh yeah, you got, oh, that's, you know, whatever. Oh, it's negative. You dropped, you know, it's like, oh, okay, I'm not totally lost. It's just like, but you're polishing, right? It's huge part of learning, creating a learning community. So I encourage you to do that for yourselves. It's great. I was reminded of you know, and just because of the background, there's a YouTube video, I think it's YouTube, and it shows this documentary on Hitler, and it's dramatized. So it's Hitler doing this stuff, and he's in the war room, and things aren't going well, whatever. And they have him speaking German, and the subtitles are all about as if he's taking a course with that book Jackson, and he's struggling, and he's just going, "Who is this guy? It's evil." Anyway, sorry, that probably didn't make any sense, but it was one of the funniest things I've ever seen.
Nice.
He was going, "Who made up these spherical Bessel functions? What is that anyway?" And I mean, of course, he's really talking about whatever, getting trounced, thankfully. Getting trounced.
I seen something similar.
Yeah.
Yeah, it was funny. It had to do with like Bitcoin, or it was a skit on Bitcoin.
Oh, yeah.
Or
Oh,
something.
really?
And he bought the wrong coin, and the coin was crashing. And so it was funny.
And that's good. I mean, what would we do with our artists, right? I mean, if we're STEM majors, there's an art to all this, and art helps us bring it to life. And I mean, it's just cool. That's the cool thing about these fields. One of the great things is, I mean, certainly economically, there's good jobs, et cetera. So go as strong as you can, make good connections, work well with others. But the people that you get to work with are interesting, and they're usually quite cool and broad-minded. And so it's that's a nice thing, and you can do it. You got to do it daily, and you got to commit to it. But it's not that long, even 2 years or whatever, and then you're at that next level, and then you go, okay, 2 more, and you start working with each other, and you just, it's never 100%, and you got your failures and this and that, but you just keep moving forward, and it's worth it, and it's better than not. I never had the image of the goal being to get a big lazy boy and just kick back all day. It's just get in and do some cool stuff. So anyway, you can do this, but do it on paper, because you never really get it until you keep drilling it. And if you go back through some of the stuff we've done, I think you will really have it polished. So as you go on, one thing that I would request is to do that survey, but also to let me know how it's going. And I wish we were on campus. My department is meeting, and we're going to be talking about, we're probably going to run labs in person if they allow us to. And we'll probably do exams on campus. So that'll be good, because it's really nice to meet you folks. Honestly, CCC is it really is special in a wonderful way, and so it's great. And the folks in our department are all really nice, and also extremely capable people. So it's a good thing. But as you go on, if you would, that's where I was going to go. If you would just, let me know how it's going, and you can send me. I'd love to know, how much it helped. I asked you that on the survey, but as you go into the physics course, if it helped, and if it didn't, you could say, hey, well, we can do this, or I don't know, whatever. But and then as you transfer and stuff, it's nice to know. And we do have this thing about, our students going on and doing well. It just feels really good. And again, I think it makes the world a better place when people come out of our community to go on. So we need it. A lot of things to solve. Let's keep this clean air going. I'm loving it.
Yep.
It's noticeable. So a lot of good stuff. Any questions? Does it feel possible? How do you feel about going into physics now?
I feel a little bit more confident. especially since I have the rest of the summer to study more.
Yeah, that's what I think. So you guys always say the right things. It's like, I wanted to say, try to, the best way to do it is do a schedule. So, and you know, so now I've got 30 minutes a day, at least I have to do guitar.
Yeah.
Now, and I'm just committing to it, you know, and I actually kind of connected with this group and it's like, okay, 30 minutes a day. You got to do some drills, you know, work on a project. And so if you do that or whatever you can do and set a minimum, something that's reasonable. I think 30 is a pretty good target because you can sit down and get into it and start and work in the puzzle. Oh, and again, I want to remind you that our brain does tend to go away from painful things and things that are a struggle. That's always true of me too. It's like, let me, you know, or, oh, this is hard. Let me just do something I know how to do. But pushing ourselves into that, the reward is really cool. And, you know, like the saying of, instead of doing tension relieving or easy fun stuff, do goal achieving stuff. And these little mantras really help us because we're engaged in pushing into something that's really profound. I mean, who's taking care of the coronavirus? STEM. I mean, I'm not putting any other people down by any means, but I'm just saying this is important stuff. So, so rock on. And
Your brain to do it. Don't play.
Exactly. And don't look at the shiny object over there. Believe me,
They'll try to find every shiny object in the room.
yeah, we're not different. You know, it's like, oh yeah, I need to dust that printer, man. I really should sharpen these pencils.
Yeah, there's plenty of stuff in my room that I never noticed until I'm actually doing something.
Right.
It's highlighted.
I know. It's great, you know, and understanding our minds and then being the boss of our minds is pretty cool.
Yeah.
And you know, and then but also connecting with others helps us too. It's all good, man. It's definitely there for the taking.
Well, it's nice when the brain cooperates.
Yeah, and there are times sometimes where you gotta go with it. I mean, sometimes you're down, you don't know why. And it's like, wow. It's like, okay, you know, and maybe you can manipulate that and put on some music that makes you feel whatever it is, you know, but you keep on going. I know a lot of people that failed their physics classes, but hopefully you guys won't be suffering that. You could, right? If something happens in life or whatever, you could still fail it. Then take it again. You know, don't give up on that. But you know, do the work and you know, contribute and enjoy. So it's worth it. And then, but you will be in a position to help out a bunch of folks next semester. And I'm sure Professor Wong in Physics 130 and Professor Liu in 120 will be asking, you know, who here took the 101, because they're going to go, oh, okay, ask Draco, you know, whatever. So, you know, and you can be a resource. I mean, I really do. I don't have to try. It's why I wanted to be at CCC. I think of it as family, and that's just cool.
Yep. Well, I'm glad that when I decided to take physics, that this was available just when I needed it.
Yeah, nice work on that.
Waited for the right time.
You did. I know. Believe me, I've been suffering for a while. There was the political climate for many years. When I was at San Francisco State, I created a course like this. It wasn't nearly as developed because I was just doing stuff. but it helped, but not like this. This is over, but just to get the course to offer it, I couldn't get it approved for various reasons, and a lot of pushback. Oh, students don't need another class to take. It's like, yeah, well, what, you want to just beat them up? I mean, it's physics. Come on. I mean, this is.
There's room for more learning.
I mean, you know, this happens across the country, across every college you want. So finally, the climate and some other things changed, and so we got it. And
Looks like a huge stepping stone. I mean, what you got there is not simple stuff, but
I know. Look at that. Look at that. Just
Yeah.
you know, it's like that's art, right? That's art. Boom, take a picture. That could be a painting, right? Actually, that's pretty cool. I never thought about it. It's like Kandinsky or something. It's like, look at this.
that's a
my,
matter.
that's my painting. I am an artist. Yeah, it's true. I kind of like that. I'm leaving that.
You know,
I got a month before classes start. That's it.
that would be a good poster shot right there. Hang on, put it on the wall.
Yeah, it's good. I'm gonna sell that. All right, that's pretty cool.
All right, then.
All right, guys. You know, guys meaning guys and gals. It was a pleasure, and do let me know how it's going. I appreciate that survey, and contact me if you need anything. Anytime.
Very well.
Thank you.
All right. You are welcome. Say hi to Brian again.
Will do.
All right.
All right, Draco.
All right, man.
Peace.
Cool.
To your classmates.
See ya.
All right.
Yeah, studying is gonna be a lot more fun reading your book.
What's that? Astronomy?
Studying over the summer is gonna be a lot more fun with your book.
Oh, is it?
Mm-hmm.
Good. I really like chapter 7. So, of course, I like chapter 8, but you don't get that one. But yeah, chapter 7's good stuff. I think you like it.
I'm sure I will.
Cool. All right. Let me know how it's going.
All right, Professor.
Okay.
I'll be looking for that email for you.
Yeah. Sounds good.
All right, then.
Okay, Richard.
All right, have a great rest of the summer.
You too. Bye.
Thank you.
Welcome. Bye, Luciana.
Bye. Be around campus sometime.
Yeah, I hope so.
All right. Enjoy the rest of your summer.
New Science Center. Yeah.
Yeah, that'll be cool.
I know. I cannot wait.
Yeah. All right. See you later.
All right. Bye.
Bye.
Hey, Jack.
So how are you?
I'm pretty good. It's fun to be able to have enough time to actually teach this stuff and go through it with you guys.
Nice.
Yeah. You seem like you've got a good background.
Yeah, because I'm a major. Because I started as so back in the day I started as a financial, like economic, like major, and then shifted like computer science. I
Oh.
learned a lot about math, like compound interest, like geometry, stuff like that.
That's
Yeah,
what it
so
is.
yeah.
You were
so I
econ?
love- So what?
You were econ?
Yeah, I was, but now I changed to like computer science. Like now I just go for computer science, like programming, coding, like stuff like that, like developing, like
Yeah. Yeah. So you've really developed that way of thinking, that structure.
yeah. I like this way of thinking a lot. Like I like the way I call this a logic. Like I like the logic. You know, you got a way to think about it. Like everything, you got an answer behind the reason, not just
Right.
showed up randomly say, oh, that's a reason, and then that's the answer. There's nothing to support or back it up. You know,
Yeah.
I don't like that.
Totally agree. You're definitely in the right fields. I agree. And then for some people, you have to train them to appreciate that because they just want, just show me what to do.
Okay.
Like, okay, well, if you're gonna get a job where you just get shown what to do, you're not gonna make much money. But
Yeah, it's kind of like programming.
yeah, programming is like, okay, you got these general things, but now how can I, make it more efficient or?
It's kind of lame for me to think right now because like programming is kind of like labor jobs. I'm not, no offense, but what I'm saying is like you just need to like repeat it over and over, like repetition. That's all. Like you just need to repeat it as much as you can, and once you repeat like enough, you got like the highest like skills.
Yeah.
And then,